So section 6.4 is integration tables. And these really are for integrals that can't be done by hand. That's not entirely true. There's definitely a couple homework problems that ask you to use the integration tables where they're integrals that you actually could do by hand if you really have the time and motivation to do so, but or the technique. So like, for example, let's look at this integral, the square root of x squared plus 25 dx. So the idea is you essentially have to look at the table and identify a formula that this kind of looks like. So this is formula number 21 on page 418, or might not be the same page. Okay. My older book, it's page 418. It might be a slightly different table, but it's in section 6.4. There's a table of like integral formulas. So here's the formula we're going to use. It's the integral of the square root of u squared plus or minus a squared du is equal to 1/2 times u times the square root of u squared plus or minus a squared plus or minus a squared times the natural log of the absolute value of u plus or minus the square root of u squared plus or minus a squared. So the idea is we have to look at our integral and say, okay, from the table, what's the form on the table that is closest to what we have? Whatever x is, or like something that looks kind of like x, should be playing the role of u, and whatever a is supposed to be a constant. So u is definitely the variable thing, and a is representative of a constant. So in this particular problem, we would say, all right, we're going to let u equal x. Our du is going to equal dx. It's actually kind of like doing a u substitution. And we need a squared to equal 25, which means a is going to be 5. The formula does specify that a is greater than 0. So just right. And then we're literally just going to replace everything in this formula with what we said. So instead of having u and a, we're going to have x and 5. So I'm going to say that the integral of the square root of x squared plus 25 dx is going to equal, well, I'm going to have a 1/2. My u is x, so it's going to be x times the square root of x squared. It is a plus, right? If it's a plus here, it's a plus here. And then a squared is 25 plus 25 times the natural log of the absolute value of x plus the square root of x squared plus 25. Close that absolute value. So kind of funky. Where'd you go? Sorry. Here's the attendance form again in case you need it. So that's the idea with the integration table, is you're basically saying, okay, I'm going to look at this integral and someone's going to give me like a list of possible formulas we can use, and then we're just going to have to kind of figure it out. So let's look at another example. So let's say we want to do the integral of the square root of 9x squared plus 4. And actually, let's look at the table for just a second. So here's the table. Here's the part of the table of integral, right? It's a long table. So I see, all right, we've got the square root of 9x squared plus 4. So I'm looking for the square root of my variable squared plus some constant. So looking at this table, well, I don't want forms involving a plus bu because that doesn't have my variable squared. So I'm going to look down here for forms involving u squared plus or minus, the square root of u squared plus or minus a squared. So if I look at that, I want this first formula again. Right? It's the same formula as last time. It's my variable squared plus or minus a constant squared. So same formula. I don't think I need to write it out again, or I can in fact just put it right back there. But now, instead of letting u be x and a be 5, I need to let u equal 3x so that u squared is 9x squared. And a needs to be, well, a squared needs to be 4, so that a is equal to 2. And importantly, and this is kind of the part that people miss a lot of times when they're doing these integration table problems, is we also need to adjust the du. So du is going to equal 3 times dx, so that 1/3 du is equal to dx. So there is kind of a u substitution aspect to these trig table, or sorry, integration table problems. So again, using this formula with u equal to 3x, actually, let's rewrite it before I get so carried away. So I'm going to rewrite this as the integral of the square root of u squared plus 2 squared, and my dx is going to be 1/3 du. So then that's going to equal 1/3 integral of the square root of u squared plus 2 squared. And then I'm going to throw the formula at it. So it's going to be 1/3 and then times all this. So it's going to be 1/2 times u, but my u is 3x. Sorry, times the square root of u squared, which is 9x squared. It's again a plus a squared plus a squared times the natural log of the absolute value of u plus the square root of u squared plus a squared. And I suppose we should probably be throwing in a plus c. Sorry, I see that you can't quite see that there. Let's look at another example. So again, these problems are not my favorite. They're really no one's favorite. Like they're kind of like, yeah, okay, there's these problems. We can look at the table sometimes. It feels, again, kind of like, sure, you can look at the table, but also there's this thing called the internet. And instead of looking this up on a table, you could just as easily Google it, right? I mean, it's kind of like once you start using outside resources, why wouldn't you use the most powerful outside resource you have? But someone may ask you a question like this. So let's look at a couple other examples. Let's say we wanted to try to calculate the integral of the square root of x squared plus 6x dx. So now, if you look back at the table for a moment, I see, well, let's see, I definitely want square root. Let's see, do I have anything on this first page? Nope, no square root ones on the first page. So I'm looking at the second page here. And the only ones where I really have square roots are right here. But they're all like the square root of u squared plus or minus a squared, right? I don't have like a u squared plus 6u. So the idea is if I've got this kind of thing, I need to modify my integral. So I need to have something squared plus or minus some constant squared. So what I actually need to do here is I have to complete the square. And this is a common technique for these kinds of problems. So we're going to rewrite this as the integral of the square root of x squared plus 6x. And what do I need to add on that's going to help me complete the square? I may have been a while, but it's like half of 6 divided by 2, which is 3, and then 3 squared is going to be 9. So I'm going to add 9, but if I add 9, I also have to write. So then the idea here is that this x squared plus 6x plus 9 is x plus 3 quantity squared. So now I can rewrite this as the integral of the square root of x plus 3 squared minus, instead of writing minus 9, I'm going to write minus 3 squared just to really emphasize that we're using, again, this same formula that we used before. So now we're in the situation, right, where, let's do this instead, right, if we're doing this, right, we're going to use this formula where now our x plus 3 is going to be our u. So we're going to let u equal x plus 3, and our a is going to be positive 3. And now this formula has a minus in it, so it's going to be the one with minuses. So it's going to be the square root of u squared minus a squared, we're going to get 1/2 u squared minus a squared natural, right? It's the whole thing with minuses. So we're going to get the answer to be 1/2 times our u. Whoops, can you see that? Yeah, you can see that. Okay. I know things are a little shaky here. So you might want to see the formula. I guess I can fold this. Sure. And unfold it later. Okay, so we're going to have 1/2 times u, which is x plus 3, times the square root of u squared minus a squared. So it's going to be x plus 3 squared minus 9 minus a squared times the natural log of the absolute value of u minus the square root of u squared minus a squared plus c. I have that plus c. So kind of interesting. Let's look at the cup, but really, again, it's really just, it's testing your ability to recognize patterns. So the idea here is really, I'm going to look at this and say, okay, like, do I see a pattern? So let's look at like 2 or 3 more examples, and then we will talk about something else. Let's say we have the integral of x divided by the square root of x to the 4th plus 2x squared plus 2. Well, that looks gnarly. If I were doing this problem, I don't know, I might try some crazy stuff first, but eventually I might roll around thinking, oh, I probably need to complete the square, right? I guess I should say, right, if we're in the context of needing to use one of these tables, you really need like something squared plus or minus some constant squared. That's often the pattern we need to recognize. So we're going to rewrite this as the integral of x over the square root of x to the 4th plus 2x squared plus 1, because half of 2 is 1 and 1 squared is 1. And then instead of saying minus 1 plus 2, we can just do the arithmetic and say minus 1 plus 2 is also 1. So then this part here, that's our x squared plus 1 quantity squared. Sounds like something interesting is happening over there. Like, really, I'm curious what's going on. Oh, well. So then we can rewrite this as the integral of x over the square root of x squared plus 1 squared plus 1 dx. Now, looking back at our formulas, this doesn't quite look like anything I have, right? If we look at our list of formulas here, I have some forms involving the square root of u squared plus or minus a squared. So it looks like I'm going to have to like kind of let u be the x squared plus 1, which will work out okay because then my du will be 2x and it'll kind of probably work. But if I look at these formulas, I want something with the square root in the denominator. So maybe I want like either it might be formula 25, it might be formula 26. What I really need to do before I can do any of these formulas is I need to do the u substitution. So let's make the logical choice for u. We're going to let u equal x squared plus 1. Our du is going to be 2x dx. So then our 1/2 du is equal to x dx. And then also our a, well, I guess we're not related to a yet. So let's just rewrite this. This is going to become 1/2 du instead of x dx. And then we're going to have 1 over the square root of u squared plus 1. And then we can totally see that, oh yeah, formula 25 is looking pretty good. Formula 25 is for the integral of 1 over the square root of u squared plus a squared, or minus a squared. So we can just throw that formula out. I know, again, it's kind of ridiculous. So formula 25 says that the integral of 1 over the square root of u squared plus or minus a squared du is equal to the natural log of the absolute value of u plus the square root of u squared plus or minus a squared. So our integral, bless you, 1/2 times the integral of 1 over the square root of u squared plus 1, or really 1 squared, is going to equal 1/2 times the natural log of the absolute value of u plus the square root of u squared plus 1 squared. Let's see. But then we need to plug in what our u value was. That's going to be 1/2 times the natural log of the absolute value of u, which was x squared plus 1 plus the square root of x squared plus 1 squared plus 1. Okay, let's do one more. Let's try to keep papers in order. Never enough room over here. Sorry, not your problem, my fault. Okay, so let's say we wanted to do the integral, oops, need your pen, of x times the square root of x to the 4th minus, actually, you know what, I'm going to change this one up just a little bit. Sorry, apologies. Do something slightly different. Let's say we want to do the integral of x squared times the square root of x to the 6th minus 36. Again, we are in the context of we are using these integration tables. So I have the square root of some stuff, and this definitely doesn't look like what's in the tables, right? The tables have like u squared in the squares. I think that, in fact, if you look at looking at this table, I think for the square root ones, right, the only thing you can really have in a square root is u squared, right? There's no like u cubed or u to the 4th or u to the 6th. So what that tells me is I need this to be like a u squared. So that's hinting at a u substitution. If I need u squared to equal x to the 6th, then what's my u sub going to be? Or what's my choice for u have to be? Right. Also, there's another clue that that's the right choice, right? If you've got an x squared there, then probably u being x cubed is logical because the derivative of x cubed is going to be 3x squared, and that's going to take care of that extra x squared out there. So then our du is going to be 3x squared, and 1/3 du is going to be x squared. Forgot the dx. So we're going to rewrite this as the integral of, let's say, about a 1/3 du. Then I have the square root of u squared minus 6 squared. And then looking at the tables, this is again formula number 21. Guess those I already have already go here, so I might as well use it. So once again, here's formula 21, one's favorite. So let's see, so that's going to end up being 1/3 times the square, so it's going to be, let's see, a 1/2 times u times the square root of u squared plus, sorry, not plus, minus, apologies, 6 squared. And then we're going to have minus 6 squared times the natural log of the absolute value of u minus the square root of u squared minus 6 squared. And now I probably should have from the very beginning just plugged in what u was equal to. So now let's go actually write our answer. 1/3 times 1/2 times x cubed times the square root of x to the 6th minus 36 minus 36 times the natural log of the absolute value of x cubed minus the square root of x to the 6th minus 36. What a not fun formula to look at. Oh, plus c. If you're really curious, you could check this by taking the derivative of it. I don't recommend it, but if you're like, oh, I've got free time, got nothing better to do, take the derivative of this, and you'll see that if you once you simplify it, it actually does equal this, which is kind of neat. So that's kind of the quick kind of overview of how these integration tables work. You're basically just looking to make what you have look like a formula that you recognize. Questions about that, either from you, Devin, or from anyone on the Zoom? Okay. Oh, sorry. You look at you raising your hand. Apologies. Let me look at one other thing here. So with that in mind, I think the rest of our time is probably best spent just doing some review, right? I mean, we could do more midpoint and Simpson's rule stuff, but that doesn't really feel like an excellent use of our time. And I feel like that stuff really, not, at least according to what that says, it's really not part of what might be on your. So yeah, I guess, okay, that's not entirely true. I guess the midpoint rule would be on there. We'll see. I think our practice is better spent elsewhere. But if you want me to do a midpoint rule or Simpson's rule or any other kind of estimating problem, let me know and we can certainly cover that. But I'm going to go ahead and do some practice. So let's say we want to do the integral of e to the 3x plus 4 plus 5 over 6x plus 7. So a couple things to be aware of here. Can we break this up into two integrals? Sure. Do you have to? Not really, but you certainly can. You might want to, just to make it easier to deal with each piece. Each of these integrals, you could do a u sub for, right? You could totally say, here I'm going to let u equal 3x plus 4, here I'm going to let u equal 6x plus 7. I don't think that's required, but if we want to show that work, here's what it would be. So for this first integral, if u equals 3x plus 4, our du is going to be 3 dx, so 1/3 du is equal to dx. And so this integral is going to become the integral of 1/3 du times e to the u, which is going to equal 1/3 e to the u, which is going to be 1/3 e to the 3x plus 4. Which we already knew was going to happen because we know that when you integrate e to a multiple of x, you get that same thing, but you end up dividing by the coefficient of x. For this one, we would let u equal the denominator, 6x plus 7. The du is going to be 6 dx, 1/6 du is equal to dx. So this integral is going to become the integral of 5 over u times 1/6 du. Or as I would probably prefer to write it, 5/6 times the integral of 1 over u du. That's going to be 5/6 natural log of the absolute value of u, which is going to equal 5/6 natural log of the absolute value of 6x plus 7. So then our whole entire answer is going to be that the integral of e to the 3x plus 4 plus 5 over 6x plus 7 dx is equal to 1/3 e to the 3x plus 4 plus 5/6 natural log of the absolute value of 6x plus 7 plus c. I don't think you should have to show your work for this. Like, I think it should be perfectly reasonable to be like, oh yeah, I know the integral of e to the 3x plus 4 is e to the 3x plus 4 divided by 3. I know the integral of 5 over 6x plus 7 is 5 natural log of the absolute value of 6x plus 7 divided by 6. But depending on what your instructor is looking for, you might need to show more work than just saying what the answers are. Let's look at some more examples. By the way, these are examples from a Co-16. So these are from the Co-16B midterm 2 review problems, which if they're not posted on the Canvas for this class, I will make sure they are posted. I grabbed them from somewhere else. I didn't actually check to see if they are posted on Canvas, but I will check after class and I will make sure that they are there if they're not already. So let's look at the next one. The integral of x over 4x plus 3 squared. dx. So this definitely has the hallmarks of a u substitution. There are things trapped inside parentheses, which means that's probably a good case for letting them equal u. U equals 4x plus 3. Du is going to equal 4 dx. And then 1/4 du is equal to just dx. So this integral is going to become the integral, So I see what to do with dx, right? Dx is going to be 1/4 du. And I see what to do with the 4x plus 3 squared. That's going to be u squared. But what about the x right there? What do I have to do with that? Well, we have to do a back substitution. Right? If you're doing a u sub and you have leftover x's that don't seem like too terrible to deal with, usually taking this u and solving for x. So u minus 3 equals 4x, and then 1/4 times u minus 3 is equal to x. That's what we're going to plug in for x. So this is going to end up equaling the integral of 1/4 times u minus 3 divided by u squared times 1/4 du. I would bring out both multiples of 1/4. So I'm going to write this as 1/4 times 1/4 times the integral of u minus 3 over u squared du. This is definitely an improvement, because if you have a rational function where the denominator only has one term, you can divide each thing by the denominator. This is going to be 1/16 times the integral of u over u squared minus 3 over u squared, which I would then write as 1/16 the integral of 1 over u minus 3u to the negative 2. Most of the time, I write things as u to a negative power, unless it's u to the negative first. For some reason, I just find it easier to think of 1 over u having an antiderivative of the natural log of the absolute value of u instead of u to the negative first. But whatever works for you. So we're going to get 1/16 times the integral of 1 over u, which is the natural log of the absolute value of u, minus 3 times the integral of u to the negative second, which is u to the negative first divided by negative 1. Let's see. I would definitely rewrite this part here, negative 3 times u to the negative 1 over negative 1, as positive 3 divided by u. And then replacing the u's with what they're equal to, this is going to equal 1/16 times the natural log of the absolute value of 4x plus 3 plus 3 divided by 4x plus 3 plus. Questions about that one? Okay. That's a lot. So let me ask you all on Zoom. For this next question, the integral of x squared plus 6x plus 4 divided by x plus 3, what do I kind of have to do to start off, right? There's only really one choice here. Anyone have any thoughts, suggestions? Again, no one else will see what you write if you want to write something. It's really hidden very well, so you can give me wrong answers. I can be like, wrong answers only. Can someone give me a wrong answer? What should I not do here? Guys, like, if we just wait long enough, just tell us the next one. Okay, Devin. Right, exactly. We definitely need to do, for those of you that might not have heard it on Zoom, long division or polynomial division, whatever way you want to call it. Polynomial long division. I suppose if you really, really, really wanted to, you could do synthetic division. I'm not a fan of synthetic division, but it does have its time and place. But really, for these problems, you want to do it the long way. So we're going to have x plus 3 dividing into x squared plus 6x plus 4. Something I've noticed over the years is that when you're doing this long division, basically, you have to do as many steps. So the degree difference here is 1, and I'm going to have to do 2 steps, most likely. Sometimes you only have to do one, but basically whatever the difference in your degrees is, you have to do that difference plus 1 iterations of the division. So x goes into x squared, x times x is x squared, x times 3 is 3x. We subtract x squared minus x squared is 0x squared, 6x minus 3x is 3x. Bring down the 4, do it all again. X times 3 gives you 3x, and then 3 times 3 is 9. Subtract 0, 4 minus 9, negative 5. So we're going to rewrite this as the integral of x plus 3. So I will admit this example is not my favorite because, right, you're getting an x plus 3 there and x plus 3 there. So I just want to point out this x plus 3 is what's going right there. And then we're going to get plus negative 5 divided by x plus 3. This x plus 3 is what's going down there. So it's always your quotient plus your remainder divided by your original divisor. And then we integrate. So this is going to end up being x squared over 2 plus 3x minus 5 times the integral of 1 over x plus 3, which is the natural log of the absolute value of x plus 3. Let's see. In contrast, what if we flip it over? What if we want to do the integral of x plus 3 over x squared plus 6x plus 4? So the place where your brain might go first. Okay, well, actually, let me just ask, what's one thing we could try? Right, exactly. Your brain might go there first. You might say partial fractions. Now, the thing about partial fractions is we have to both, well, first of all, the degree on top has to be less. Okay, it is. And second, and importantly, the denominator has to factor. And I don't think this denominator factors. So, but I agree, right? I would look at this and be like, well, it looks like a kind of partial fractions kind of thing. But before we do partial fractions, in fact, actually, we could even make it a little bit more suggestive here. Or if we wanted to do this integral instead, x plus 3 over x squared plus 6x plus 5. This one, we totally could do partial fractions because the denominator definitely does factor, right? X squared plus 6x plus 5. This certainly factors as x plus 5 times x plus 1. What I want you to remember is before you jump to partial fractions conclusions, you really want to explore the possibility of a u substitution. So for this problem here, we could try letting u equal the denominator, x squared plus 6x plus 4. And oh yeah, our du is going to be 2x plus 6 dx, and that is exactly 2 times x plus 3 dx, which is great. That means that 1/2 du is equal to x plus 3 times dx. So I can rewrite this integral as the integral of 1/2 du over u. Or if you prefer, 1/2 integral of 1 over u du. So that's simply going to be 1/2 times the natural log of the absolute value of u, which is going to be 1/2 times the natural log of the absolute value of x squared plus 6x plus 4 plus c. Let's look at this other one for just a second. So let's say we wanted to try and do the integral of x plus 3 over x squared plus 6x plus 5. We could totally do this one with the u sub as well. If you did the u sub letting u equal the bottom, your answer would end up being 1/2 natural log of x squared plus 6x plus 5 in absolute value. We can check. The derivative of that is equal to, let's see, 1/2. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. and the derivative of c is 0. And then, oh, look, 1/2 times 2x plus 6, that's exactly going to be an x plus 3 over x squared plus 6x plus 5. So the point of this problem is that you should look for a u sub first. Because if you can do a u sub, we usually think of that as being the easiest way to do it. However, you could use partial fractions. So let's say you missed the u sub because you just aren't looking for it. Partial fractions will work here. So if we want to do this as partial fractions, we're going to have x plus 3 over x plus 5 times x plus 1. I do have to stress, you can only use partial fractions if the denominator factors. If it doesn't factor, like in the previous problem, we couldn't use partial fractions. So this one's going to be a over x plus 5 plus b over x plus 1. And then we're going to we're going to multiply both sides by our common denominator. I really do encourage you to write this step if you have to do partial fractions. It helps you remember what's going on. So when you multiply this by that, you're going to get just x plus 3. When you multiply this by that, the x plus 5s cancel and you get a times x plus 1. When you multiply this by that, the x plus 1s cancel and you get b times x plus 5. And then we really should, in my opinion, use the convenient values of x method. So I'm going to set x equal to -1. I'm going to get -1 plus 3 equal to a times 0 plus b times 4. So -1 plus 3 is 2. That equals 4 times b. So b is going to equal 2 divided by 4, which is 1/2. I should ask, did you learn this method in class at all, or is it completely the other way? Okay, so what I would say is it's perfectly fine to use this method, but you should show your work, meaning you really should say, like, we should write down x equals -1 and then show the work of actually putting -1 in for each x, right? Don't kind of skip that part, because if someone's like, well, what are they really doing here? We didn't do it this way in class. If you show your work, it'll be obvious. Oh yeah, they're doing this other thing and they're not doing anything wrong, so it should still be correct. But I would recommend, 1, doing it this way, and 2, showing your work. So then I'm going to set x equal to -5, and I'm going to have -5 plus 3 equal to a times -5 plus 1 plus b times 0. So I'm going to have -5 plus 3, which is -2, equal to a times -4. So a is going to equal +1/2. So then I'm going to rewrite my integral. The integral of x plus 3 over x plus 5 times x plus 1. That's going to equal the integral of a, so 1/2 over x plus 5, plus b, 1/2 over x plus 1. And then we know how to integrate these things. It's going to equal 1/2 times the natural log of the absolute value of x plus 5 plus 1/2 times the natural log of the absolute value of x plus 1. So then we have to ask ourselves, are these answers the same? And the answer is yes, right? If you smash these two logarithms together, you get 1/2 times the natural log of x plus 5 times x plus 1. And x plus 5 times x plus 1 is exactly x squared plus 6x plus 5. So definitely the same, but I think I want to say it's pretty obvious that doing it this first way with the u sub is much easier. Right, this is a lot more work, a lot more opportunity to make arithmetic errors. Whereas if you're doing a u sub, usually it's not too terrible. So once again, a big plug for always look to see if you can do a u sub before you do some other stuff. Okay. So let's look at this next one, which is the integral of the natural log of x cubed over x dx. So do be careful, right? When this says natural log of x cubed like this, if there isn't any explicit parentheses written, this means this is, I should say, this is not the integral of the natural log of x quantity cubed over x dx. Meaning we have parentheses around the x cubed. And what I would recommend doing here is first and foremost bringing down that 3, right? We can use our rules of logarithms to say, okay, I'm going to rewrite this as the integral of 3 times the natural log of x over x dx. And in this problem, I see a mixture of types of things. I see a logarithmic function and I see a power of x. So when I see a mixture, I think I've got to do either u sub or integration by parts. And I'm always going to try u sub first because it's easier, right? A lot of integration is taking the path of least resistance, finding the method that's easiest first, and then if it doesn't work, try something else. So if we do that, we're going to let u equal the natural log of x, because the derivative of u is 1 over x times dx. And we have a 1 over x dx, right? So again, I know it's been a while since we've really talked about u substitution, but you're always looking for a choice for u whose derivative hopefully is also in there. So we're going to rewrite this as 3 times the integral of u du. And we're going to integrate. And we're going to get 3 times u squared over 2 plus c. And then we're going to plug back in and get 3 times the, I should really write it as 3 halves times the natural log of x quantity squared. Do be careful for our answer, right? The natural log of x in parentheses has to be entirely squared. This other problem, which is different, would still lend itself to the same process. If we were doing the integral of the natural log of x quantity cubed over x dx, we would still actually make the same u sub. There it is, right there. I'm not even going to write it again because it's right there. So then this would become the integral of u cubed, and then 1 over x dx is again my du. So this would just be u to the 4th over 4 plus c, which would then be the natural log of x quantity to the 4th over 4 plus c. I've got to try to make my u's look more different than my 4's. Or like u to the u over u, 4 to the, no, it's u to the 4th over 4. Okay, let's look at one, I don't know this page. Let's look at one more version of this type of problem. Let's say we have now, instead of the natural log of x cubed over x, the natural log of x over x cubed. Again, I'm going to try a u sub. So if I let u equal to the natural log of x, my du is going to be 1 over x dx. You could try to make this work, right? I could say, well, okay. So the question you kind of have to ask yourself is, how far do you really want to go, right? Like we could say, well, I could rewrite this as the natural log of x over, and then I could break up the x cubed as an x squared times an x, like that. You could try that. I'm not saying you should. I'm just pointing out, like, you don't always want to give up on the u sub right away. But I'm gonna say, okay, this is my du. There's my u, and then if I'm gonna do a back sub, right? Once I start getting the back substitution, I might start thinking maybe I should try something else. But just to kind of see it out a little further, e to the u is equal to e to the natural log of x, which is x. So I could write this as the integral of u over x squared is going to become e to the u squared, and then du. This is looking not great. This is looking like the integral of u, and then that's e to the 2u, so times e to the negative 2u du. If you see this, you'll be like, well, I can see I have to do integration by parts for this. But if I have to do integration by parts for this, I should probably just go back here and try doing integration by parts for the original thing. So I probably would have stopped before I got here, but I wanted to point out you can keep going on, but you're probably going to get to someplace that's worse. So instead, let's try integration by parts. So here was our u sub attempt. It's not going to work out. So with integration by parts, I have the integral of natural log of x over x cubed dx. We're going to let u equal, of course, what do we have to let u equal to if we're doing integration by parts? Right, exactly. Always the natural log of x if you have enrichment, if you have one, right? You never want to let u equal anything but the natural log of x if you have a natural log of x. And then of course, dv has to be the entire rest. So dv is going to be some 1 over x cubed times dx. Because again, these two things have to multiply together to be the integral. So then our du is going to equal 1 over x dx. And our v, I should probably rewrite this. dv is equal to x to the negative third times dx. So that v is equal to x to the negative 2 over negative 2. Just to make it a little easier to figure out what's what. And then we're going to rewrite it. Our integral of the natural log of x over x cubed dx, which is our integral of v du. That's not right, James. Sorry. That's our integral of u dv. Apologize. That's going to equal our ultraviolet super voodoo. Our u times v, so natural log of x times x to the negative 2 over negative 2 minus the integral of v du, x to the negative 2 over negative 2 times 1 over x dx. And once again, the whole point of integration by parts is that this new integral got simpler to evaluate, or should have gotten simpler to evaluate. So let's see, simplifying this a little bit, I'm going to rewrite this first part as natural log of x divided by negative 2x squared. I probably would actually put the negative out in front, but too late. And then I'm going to bring this negative 1/2 out in front as well. So minus a minus 1/2 is going to be plus 1/2 integral of x to the negative second divided by x is going to be x to the negative third. This kind of thing always happens when you have an integration by parts with a natural log of x and an x to a power. You always end up getting an integral at the end that's the same as like the dv you already did before. So right, I'm going to integrate x to the negative third. Oh, I've already done that. It's x to the negative 2 over negative 2. This ends up equaling negative natural log of x over 2x squared plus 1/2 times x to the negative 2 over negative 2. And then if you cared to simplify this, I would, sorry, just one second. I can't see the thing I'm trying to look at here. Yes, I'm off. That's okay. If you cared to simplify this, I would write this as negative natural log of x over 2x squared minus 1 over 4x squared. Let's see. Okay. Let's look at a couple more. So let's look at the integral of x cubed times e to the x to the 4th. Again, we see a mixture. Actually, let's make this one definite. Let's do the integral from 0 to 1 of x cubed e to the x to the 4th. So, well, whether it's a u sub or integration by parts, I should certainly try a u sub first. So I'm going to try letting u equal, I'm going to make a small change to my limits of integration. I'm going to go from 0 to 2. I'm going to let u equal x to the 4th. So then my du is going to be 4x cubed dx. And oh yeah, that's looking worthwhile, right? Things are going to work out okay. So my 1/4 du is going to equal x cubed dx. So we have choices. Choice 1, don't change your limits of integration. You can say, okay, this is going to equal the integral from x equals 0 to an x equals 2. And then my x cubed dx is going to be a 1/4 du times e to the u. That's perfectly fine. It's not the choice I would make, but it's fine. And then we integrate, we get 1/4 times e to the u from x equals 0 to x equals 2. And then we plug back in what u is equal to. So it's 1/4 e to the x to the 4th from x equals 0 to x equals 2. And then we get 1/4 times e to the 2 to the 4th, which is e to the 16th, minus 1/4 times e to the 0. And simplifying this, I guess, a tiny bit more, you get 1/4 times e to the 16th minus 1. Or change the limits of integration. I'm going to write this as 1/4 times the integral of e to the u. But instead of writing x equals 0 to x equals 2, let's actually change limits of integration. So we know that if x equals 0, u is going to equal 0 to the 4th, which is 0. And if x equals 2, u is going to equal x to the 4th, which is 2 to the 4th, which is 16. So those are my new limits of integration. And now the nice thing about that is I don't have to change back at the end. So I can just integrate this. I get 1/4 e to the u from 0 to 16, and then I just plug in 16 and 0. So I get 1/4 times e to the 16th minus e to the 0, which is 1/4 times e to the 16th minus 1. Either way is good. I prefer to do it the second way, but you don't have to do it that way. Versus this other problem, the integral of x squared e to the 3x dx from 0 to 1. So we could try a u sub. It's not going to work out, right? If you let u equal 3x, your du is 3. You're still going to have essentially x squared times u squared times e to the 3u or u to the u. So definitely integration by parts. We could use tabular here, although again, I don't think that's something you've actually talked about in class. Is that correct? Okay. So if someone asks you this question on a test, you should probably actually go the long way. And so if I was doing this, I would do the indefinite integral first. So let's see, my u is going to be x squared. My du is 2x dx. My dv is e to the 3x dx. And my v is e to the 3x divided by 3. So then our integral of x squared e to the 3x dx is going to equal u times v minus the integral of v du, which is going to be e to the 3x over 3 times 2x dx. And then we have to do integration by parts again. And at this point, people like to do different things. I like to factor out the 2/3, other people don't. I'm actually going to, I feel like it's actually easier to keep track of things if we don't. So I'm just going to rewrite this a tiny bit. I'm going to rewrite it as x squared e to the 3x over 3 minus the integral of e to the 3x times 2/3 x dx. I'm going to let this be my u and this be my dv again. So now u is equal to 2/3 x, du is 2/3 dx, dv once again is e to the 3x dx, and v is e to the 3x over 3. So now I write this out. So here's what we've got. I've got this integral here, and that's going to equal, I still have the x squared times e to the 3x over 3. Minus, now I'm going to do all of the ultraviolet supervoodoo. So it's going to be the ultraviolet supervoodoo. So it's going to be minus all of uv minus the integral of du. The point I'm trying to make here is that we have to make sure that we distribute the minus sign. So uv, that's going to be 2/3 x times e to the 3x over 3 minus the integral of v du, which is going to be e to the 3x over 3 times 2/3 dx, sorry. Let's simplify it a tiny bit. We get x squared e to the 3x over 3 minus 2/3 times 1/3 is 2/9 x e to the 3x minus the integral of e to the 3x is e to the 3x over 3. So I'm going to have a, let's see, a 2/9 times the integral of e to the 3x is e to the 3x over 3. Cool. So then we can go back and say, all right, the integral from 0 to 1 of x squared e to the 3x dx is this whole thing, x squared e to the 3x over 3 minus 2/9 x e to the 3x minus 2/27 e to the 3x, evaluated from 0 to 1. Yes. Yes, it would. Thank you. So you got to remember to distribute that minus sign. And then we plug in. So actually, you bring up a good point, which we're going to check in just a second as well. But yes. So plugging in. Sorry, it's hard to get all these things up there. So we plug this in. We're going to get, so plugging in 1, I'm going to get 1 times e to the 3 over 3. So e to the 3 over 3 minus 2/9 times 1 times e to the 3rd plus 2/27 times e to the 3rd. Now be careful. I was helping a student with a problem like this the other day. When they plugged in 0, they got all zeros, but you actually don't. Because when we plug in the 0, we end up getting 0 minus 0 plus 2/27 times e to the 0, which is 2/27 times 1. And then you could probably simplify this if you really wanted to. You could say that you have, getting a common denominator, 9e cubed over 27. I should say, if you're doing a test, right, you should stop here. And then if you really have all the time in the world at the end, go back and get a common denominator. But like, this is a perfectly fine answer. If you want to get a common denominator, 9e cubed over 27 minus, multiply this by 3 over 3, and you get 6e cubed over 27 plus 2e cubed over 27 minus 2 over 27. So putting it all together, you get 9 minus 6 is 3 plus 2 is 5. So 5e cubed minus 2 all over 27. What I was going to say about me missing this minus sign turning into a positive sign for the student here is one thing we could have done to check that our work was right is we could have done a quick tabular. We could have been like, okay, tabular, u is going to be x squared, derivative is 2x to 0, dv is e to the 3x, and then integral is e to the 3x over 3, e to the 3x over 9, e to the 3x over 27. And then we know it's going to be plus, minus, plus. So yeah, you'll be like, okay, it's plus x squared e to the 3x over 3, check, minus 2x e to the 3x over 9, check, plus, oh, I had a minus sign. It should have been a plus 2 e to the 3x over 27. So that's a good check. I can't recommend using tabular without explicit permission from your teacher, even though it's valid, but it can certainly be used as a check for your work. You could also just use it, take right. You could risk it, be like, yeah, I'm going to use it anyway. I mean, it works. Let me see one thing here. Just want to be like, so we're not doing any. I just want to make sure this. We're not talking about any area or volume stuff. Guess not. I guess you can talk about area. Volume. Has Bert covered volume yet?
Yesterday, yeah.
Okay. Okay. But area might be, right? Area between curves? Seems reasonable. Okay. We'll talk about volume on Thursday. I mean, I know we talked about volume like a long time ago, like because of the other concepts. We can definitely talk about volume again. But let's look at this question here. Let's set up the integral for the area between, what have I got here? Sure. Y equal to x squared plus 1 and y equal to x plus 7. So we do not have to draw a picture, but you certainly can if you want to. Let's do it without drawing the picture first, and then we'll see what the picture kind of gives us. So we know we need the integral from a to b of some function dx. So to find the limits of integration, we need to know where these functions intersect. So we set x squared plus 1 equal to x plus 7. Bring everything to a convenient side. I'm going to bring it to the left. So x squared minus x, 1 minus 7 is minus 6, equal to 0. And this typically this will factor if someone's been kind. So we have x minus 3 times x plus 2 equal to 0. So we're going to get x equal to 3 and x equal to negative 2. So our integral is looking like the integral from negative 2 to positive 3. And then typically it should be the top minus the bottom. So this f of x here should be the top minus the bottom function. Or if you're doing left and right, it should be the right minus the left. So top minus bottom, all right. How do I figure out which functions on top without drawing them? You pick a point between negative 2 and 3, or between whatever your intersection points are. So if I set x equal to 1, well then the first function is going to be y equal to 1 squared plus 1, which is 2. And the second function, y equal to x plus 7, is going to be y equal to 1 plus 7, which is 8. So clearly, y equals x plus 7 is the larger function on this interval. So what we're going to do is we're going to say, okay, we're going to do the integral from negative 2 to 3 of x plus 7 minus x squared plus 1. And that's how we would set this up. I will also point out we could totally have drawn a picture. X squared plus 1 is a parabola that opens upward, has a vertex at the point 0, 1. It doesn't have to be a good picture, it just has to be like decent. And then y equals x plus 7 is a straight line. It goes up from left to right, and the y-intercept is 7. So I don't know, it's gonna look something like this. There's my y-intercept is 0, 7. There's my, and then we can see, oh yeah, look, if I'm looking at the area between them, the picture does kind of show us pretty obviously that the top function is y equals x plus 7, and the bottom function is y equal to x squared plus 1. And the idea is, right, we're adding up all these rectangles. All right, let's do one more. So this problem, I will point out, it's very possible you will have a question that says set up an integral, but don't actually solve it. So if it just says set up the integral, that's all they're asking you to do. I'm not asking you to actually do any more. You certainly, we could evaluate this one. It's not hard to integrate this or plug in some integration, but definitely don't do more work than you need to do on a test. Like something that says just set up the integral. It'll usually be like in my gosh, capital letters like set up, but do not evaluate the following integral, right? Make sure you look for that because you don't want to do extra work that's not going to count for anything. Let's look at one more setting up one. Let's set up the integral, but do not evaluate for the area between, sure, x equal to y squared plus 4 and x equal to 9. Yeah, that's it. That's all I got. And I do think we should graph it just to kind of see what's going on. Although you can totally get away without graphing it. But let's graph it. So x equal to y squared plus 4. that is a parabola type thing, but which way does it open? Up, down, left, right? If you're not sure, and sometimes I'm not sure, I start plotting points. So this one's a little weird to graph, right? Because it's x is a function of y. But I'm going to start with setting y equal to 0. So if y equals 0, y equals 0, x is going to be 4. Okay, and then if y is 1, x is going to be 1 plus 4, which is 5. So I'm going to get the point 5, 1. But also that's true if y is 1 or negative 1. Right? If y is negative 1 squared is also 1, and 1 plus 4 is still 5. And then if I set y equal to 2 or negative 2, plus or minus 2 squared is 4, and 4 plus 4 is 8. So x is 4, x is 5, 6, 7, 8. So now we can kind of see, oh, this is looking like a parabola that opens to the right. So there's my parabola, x equal to y squared plus 4. And then I also need the line x equal to 9, which is one more point over. There's x equal to 9. So I'm looking for the area between these two curves. So I'm looking for that area there. There are two ways to do this problem. And I don't know how much you've talked about integrating things using horizontal cross sections versus vertical cross sections, but this one definitely is more easily done using horizontal cross sections because you already have x as a function of y. So I use a horizontal strip or cross section. The area of my strip is just the length times the height. I would really call the height here the width, right? It's like the small little width of the rectangle. So that's going to be the length, which is, okay, how long is this? Well, it depends on where I draw it, right? If I draw it down here, it's longer. If I draw it over here, it's shorter. But it's always going to be the right function minus the left function. So my length here is going to be 9 minus y squared plus 4. What's the height of that rectangle? Or I should say, what's the width of that rectangle? That very, very small width is I call it a dy, right? It's a small change in y. With my vertical strip, the previous problem, I would call this width a dx, a small change in x. So then this is the area of my strip or my rectangle, and then we are quote unquote adding up the rectangles with the integral from, okay, ooh, how far down? Oh, I didn't find how far down and how far up my strips go. So they go down, well, I know I'm integrating 9 minus y squared plus 4 dy. And I have to find how low and how high they go. Well, that's not too terrible. I'm just going to set my functions equal to each other. So set 9 equal to y squared plus 4. Subtract 4, 5 equals y squared. So y is going to equal plus or minus the square root of 5. So the lower limit's definitely when x is 9 and y is the negative square root of 5. The upper limit is when x is 9 and y is the positive square root of 5. So the lower y value is the negative square root of 5. The upper y value is the positive square root of 5. You also could do this one using vertical strips instead of horizontal strips. Should we do that? Okay. So I wish I had more room on this piece of paper. Let's draw it again. We won't draw it quite as precisely. We'll just say, okay, picture again. Parabola. Line x equals 9. And we already know that we have intersection points at 9 comma square root of 5 and 9 comma negative square root of 5. And again, we were trying to see what's going on with. But now, instead of using a horizontal strip like we did in the previous iteration, we're going to set it up using a vertical strip. And so just like before, the area of my strip is going to equal, I'm going to say length times width or base times height, whatever you want to call it. The base is a small change in x. That's my dx. The height is the, so for a horizontal rectangle or strip, the length of it is the right minus the left function, right? The bigger x value minus the smaller x value. For a vertical strip or a vertical rectangle, the height or the length of it is the top minus the bottom. Well, my top function and my bottom function are the same, right? This parabola is x equal to y squared plus 4, and this line is x equal to 9. But if I do y squared plus 4 minus y squared plus 4, that's going to be 0, which is the problem. And the problem really is this needs to be a function of x, not a function of y. So taking x equal to y squared plus 4 and solving for y, I get x minus 4 equal to y squared, and then plus or minus the square root of x minus 4, the y. So this top half of the function, this top half is y equal to plus the square root of x minus 4. And this bottom half is y equal to minus the square root of x minus 4. So then the area of my strip is going to be dx times the top, which is the square root of x minus 4, minus the bottom, which is negative square root of x minus 4. So then the total area is going to be the integral of this times this. So it's going to be the square root of x minus 4 minus the negative square root of x minus 4 dx. And then we're going, instead of going from bottom to top, we're going from left to right. So as far left as x equal to 4, as far right as x equal to 9. And the one thing I'll say about this is you usually see people simplify this integrand, because square root of x minus 4 minus minus, so plus the square root of x minus 4 is 2 times the integral of the square root of x minus 4. All right.